This last section involves the Chatelier's principles and also catalysts. I'll keep that under the same title. But Le Chatelier's principle is an idea that we use all the time in chemistry, and it's simply this: when you have a system and it's at equilibrium, right, and you do something to change the equilibrium. For example, you can change the temperature, or you can change the pressure, or you can change the concentration. You can actually even change volume of a container. Well, anytime you do that, there is a good chance that the system's not at equilibrium anymore. And Le Chatelier's principle allows us to predict the direction a reaction will go in order to get back to equilibrium. And the key to Le Chatelier's principle is this: you have a system at equilibrium, you take it out of equilibrium, and then the system, right, the reaction, right, fights to reduce that change. It'll try to compensate for the change that you make. So this is how we're going to do this, okay? In the Chatelier's problems, we assume it starts at equilibrium. We identify what's added or removed or changed, okay? And then we determine what the reaction will have to do to counteract that change. Like, for example, if you take a reactant out, right? Some of the reactants at equilibrium, take some of the reactant out. Well, then the system's no longer at equilibrium. But how does it counter that? It's going to make more of that reactant. So in other words, it's going to go left. It's going to shift to the left. That'll help us to determine the direction of change, and then we can sort of determine how everything, reactants and products, will change once we determine which way it has to shift. I'll give you an example, and this is sort of a physical analog to this kind of system. And it's just a tube like this. And the tube at the bottom could be really small. And you put water in it. So there's your water, right? And what's going to happen? Well, if there's no water on the right side, then this will drop. And eventually you'll get something like this. And you know the levels on the left and the right, they have to be the same, because it's water, right? And it's going to find a level, and the left side and the right side are going to be the same. It would even work if the left side and the right side look like that. Because water always, the top, right, wants to have a uniform pressure. And so when it has, if this left side was higher, there'd be more pressure on that side than the right side. And so it would come down until the pressure was equal on the left and the right hand side. So let's say this is our system at equilibrium, and I remove some water from here. What happens, right? Well, if you remove water from there, then what ends up happening is the water will flow in this direction. What does that mean for the other side? It'll go down, right? And the left side is going to try to counteract you removing that, and so it's going to come up and try to get to a new level, and the left and the right side will balance again, and then you'll reestablish equilibrium. Okay. So this is how I sort of give these problems, right? I lay them out. I have this reaction, and let's say it's at equilibrium, and then I use a big fat arrow like this one to say that the concentration went up, right? So this is the first thing that we're going to do. We're going to look at what was changed. So this is the first thing. The next thing we do is this. Well, if that went up, there's too much, and so it's going to have to shift to the right. So that's the second thing you do. Again, going back to this, right? The reaction assumes start at equilibrium, identify what was added or removed, determine what happens to counteract this change. That's the direction, right? That's going to help us determine direction. So if you put stuff in, it needs to come down. It's going to go to the right, let's say in this case. So if that's the case, now we can determine what happens to everything else. If the reaction is shifting to the right, these will go up. So I usually increasing arrow like that, and these will go down. So that's what will happen to the H2. Okay, so these are supposed to be in these boxes, but I don't know why I didn't put them in there like that. So what happens when I do this, right? What does that mean? It means I took some nitrogen gas out of the mixture. If I took some out, which way does the arrow respond, right? It's going to go like this. And if it goes like that, that means the reactants both. The reactants will both have to go down, and this product will have to go up like that. Okay, so I'm going to pause it, and you can do the next two, and then we'll talk about the third one. Okay, so there are all the arrows in place, right? So the first thing I look at is this, right? Or sorry, not that. This. What did I change? And then I determined that it had to go to the left because I took some out. That means if it's going to the left, then the NO will go up, and the N2 and the H2 will go down. H2O will go down. And in this problem, the first thing I looked at was this. That was the first thing. And since that went up, oh, I did it wrong. It goes got to go this way, which means all these arrows are wrong, right? Which means this has to go down, and this has to go up, and this has to go up. So that's the sort of the nature of Le Chatelier's principle, is how you determine whether or not a reaction is going left or right, and then what are happening to all the other components in the solution. Now, having said that, right, what happens if I decrease the volume, right? If I decrease the volume, and it's a gas, so the gas molecules all get closer together. Now, what does that mean? It means when you decrease the volume, the concentrations of everything goes up, okay? As it turns out, if you think about the way this reaction is set out, you notice that there's 4 moles of gas on here, and there's 3 moles of gas on here. So if I'm increasing the pressure on both sides, right, and I have different numbers of moles in the reaction, the side with more moles has more of a motivation to be gotten rid of, right? Because the whole idea of Le Chatelier's principle is to get rid of what or compensate for a change. And so since there's 4 moles trying to compensate versus 3 moles, then what will happen is if I decrease the volume, the reaction will shift in this direction. And then the products will go up, and the reactants will go down like this. Now, the same thing is true, the same principle is true, right, if I increase the volume. But in the case of increase the volume, you're taking away the concentration, you're lowering all the concentrations because the volume's getting bigger. And so it'll shift to the side that has actually more moles. So if I increase volume, then what happens, it'll shift in that direction, and all the changes are then reversed. Okay, so let's talk about what happened. Let's summarize again what happened. So when I say increasing pressures, it actually means decreasing volume. Okay. That means that causes a shift to product molecules, or shift to fewer, this should actually be moles here, fewer moles. And if I decrease the pressure, that's increasing volume, right? That causes a shift to more moles. So in other words, here's 2 here, here's 4, right? So if I decrease the volume, that'll shift and make the pressures all greater. It shifts to the right for this reaction. And then if I increase the volume, it'll go to the side for more moles. And so for this reaction, it would, the one that's listed here, would go to the left, right? Okay. Now, temperature can also affect equilibrium. And if you go back and you look at it in the rate law chapter, right, reactions that are endothermic and exothermic have different activation energies going in the forward and the reverse reaction. And so increasing temperature increases the rates by different amounts, right? Increasing the temperature generally makes the rates faster, but because in an exothermic reaction, for example, the activation energies are different, it has a, for example, greater effect on one direction going back, let's say, than going forward. So having said that, it's a relatively simple kind of idea to think about. So here's an equilibrium reaction, and it's an endothermic reaction, which means there's heat on the reaction side. That's the way we think about it. Absorbing energy, get to the product, you have to absorb energy to go up in energy to the products. If you treat it like a reactant and you increase the temperature, that's this case that's right down here, that means the reaction will have to shift to the right. And if it shifts to the right, then these will go up, these will go down. Now, if you did the opposite, that is, you removed energy, then that would be this. Then the reaction would try to compensate and provide more energy. And so the result is this side would go up and this side would go down. So it's relatively straightforward on how you do that. You either heat it up, or you cool it down. Heating it up causes this reaction to shift to the right, and then cooling it down causes it to shift to the left. Now, here's an interesting idea, though. If you add this complex ion of cobalt and water, then what ends up happening is the reaction will shift to the right, just like you would have predicted before, But that means the reactants have to both go down and the products have to go up. And what happens in this reaction if you add more of the reactant and shift the equilibrium to the right? The reaction solution cools down because it's absorbing heat as it shifts to the right. On the other hand, so you could get the same kind of effect by removing this, the chloride complex of cobalt, and it'll shift to the right. And then what will end up happening is, it'll shift to the left. No, it'll shift to the right, my bad. Because I'm taking this down, so it wants to go that way, so this will go up, and these will go down. And this will go down as well. Okay, so you can use temperature to manipulate an equilibrium, but if you manipulate an equilibrium that's strongly endothermic or exothermic, and you shift the equilibrium, you'll get a temperature change in the solution because of that. Okay, so last thing in Le Chatelier's principle is something to be careful of. And these are kind of like traps that you find that are set in standardized tests, for example. They'll ask you a Le Chatelier's principle question, and they're going to ask you what various components of the reaction mixture do to the equilibrium of the reaction, So, for example, here's silver chloride, and we looked at this reaction. We looked at this reaction earlier, And it produces silver ions and chloride ions. So they'll say things like, if you remove silver or add silver, which way does the reaction shift, And those are fairly straightforward because silver ion is in solution and you're adding silver ions. If you add silver ion and a system's at equilibrium, what's going to happen? Well, it'll shift to the left. When it shifts to the left, what you're going to see is precipitation take place. And then they're going to ask you a question like, what if you take chloride out? Well, then if you take chloride out, then it'll shift to the right. And when you take chloride out, it shifts to the right. So what does it look like in the solution? As you remove the chloride, or if you remove silver for that matter, the silver chloride would begin to dissolve as it begins to shift in that direction. So you could get more precipitation by forcing it to the reactant side, or dissolving a precipitate by shifting it to the product side. And then they're going to ask you this question, and you're like not expecting it. They're going to say, and you add silver chloride to the solution, what will happen to the concentrations of silver ion and chloride ion? And here's the thing, for heterogeneous reactions you have to be careful of. Nothing happens, because if you think about it, the K for this reaction is the concentration of silver ion times the chloride ion, and the solid has no effect. Remember we talked about activity of the solid. It has no effect on the equilibrium because it's not involved in the equilibrium expression. But more accurately, the activity doesn't change because a solid always has this unit constant activity. And so by changing changing the moles of solid, you don't change how active it is, and so the solution doesn't respond by producing more ions. Okay, but a simple way to look at it is it's just not in the K expression because it's heterogeneous. Same thing's true for this particular reaction, right? This one has a K that's equal to what? It's the concentration of copper and the concentration of silver squared. So the solid copper and the solid silver are not part of the equilibrium expression. So if they say which direction does the reaction shift by adding silver metal, right? The answer is it doesn't shift. It's still at equilibrium because you're not really changing that activity of that metal. Okay, so that's one of those things I want to point out about heterogeneous equilibria. A lot of times there'll be a solid in a reaction, and one of the questions will ask you what happens when you change the concentration or the amount of, let's say, silver in the solution, or the solid in the solution, or the liquid of the solution. Well, the last thing in this particular segment to talk about is what's the effect of the catalyst? And the answer is nothing. The reactions go faster, but equilibrium is not affected. Now, if you remember, a catalyst is not consumed in a reaction, but causes the reaction to go faster. Well, it turns out a catalyst is kind of like both the reactant. If you remember the solid phase catalyst videos that we watched, it's both a reactant and it's a product because it helps the reaction take place, right, faster by binding to the metal. So it actually participates in the reaction, but then is re-released as the free metal at the end. When you write a reaction of a catalyst, it might look something. You would write the catalyst as product and reactant. When you write Kc, it would just be A over, or B over A, like this. So, because if you wrote the catalyst in there, it would cancel out. So a catalyst doesn't actually change the equilibrium concentration, it just speeds up how fast you get there.